Okay, we have just watched this video. Okay. So for those who are going to watch at home, you should watch that video. I want to talk about non-autonomous systems. Something is wrong with these letters. Non-autonomous systems. Why they are interesting? We realize that chaos appears in 3D flows, right? Now, in classical mechanics, things come in pairs, like positions and momenta, right? So there are two-dimensional systems like harmonic oscillator. Then if you go to double pendulum, let's say, you have immediately already 4 degrees of freedom, right? Because there are these two angles and their change. So how to get a 3D system, which is also nice to analyze? Well, you can take a 2D system like harmonic oscillator, let's say, and force it, right? If you put so for example, let me give you a very nice example. Forced double well oscillator. Imagine you have a system that looks like this. Okay, let me just draw it a bit like this. Yes. You have a ball here, okay, and you are basically connecting this to just something that, so you have a double well, right? So the ball is happily sitting here, but you start shaking it. Do you understand the system? So if you do that, then the equations look like this. So I should really write the equation and then show it to you. X plus delta x dot minus x plus x cubed equals f times cosine omega t. Yes, very good. What is this? Inertia, right? This is inertia. This is friction, right? Yes, exactly. The same idea. This is double well potential, force of the double well potential. Double well potential looks like x to the 4 plus x to the square, some numbers there. But if you take the derivative of that, you get this minus x plus x cubed. Why it is important? Because it's nonlinear. As you can see here, this is nonlinear, right? So far, on the left-hand side, we have a nonlinear 2D flow, right? But including this time, if you remember just in the beginning when we started dealing with this, we said that either you look at it as two-dimensional flow that is being forced, and hence it's non-autonomous, or you put the forcer into the system and just define x3, which is equal to t, and then x3 dot is equal to 1. That way you get a three-dimensional system, right? So in three-dimensional system, we expect to get chaos. All right, very good. And I just happen to have a code for it somewhere here. Oh, it's gone. Let's find it. Shared chapters, Lawrence, codes, Here it is. Python again, yes. So, what do we have here? We have these parameters. There is the force, there is the omega dt, the b in front of the friction part. We start from initial condition and okay, let me just run it and you will see very nice thing going on. There you go. So what is this? What are we watching right now, right? I will tell you. What we are watching is the Poincaré section. That's what I was about to explain, right? Now, this system is three-dimensional, yes, but we can think of it as like the time. So this, if omega is 1, then period is 2 pi, right? So we are expecting the system to do something similar every 2 pi. So we can plot the system, although time actually is a third dimension and it goes on forever, but we can just bring it back to itself, okay? Watch it stroboscopically. Do you know the stroboscope? Do you know what it is? It's like something like this, then it has like ridges around it. I don't know if your physics lab had one of these or not. So you basically look from here, you rotate the thing. I didn't put the all ridges. You can imagine that there are ridges everywhere, right? If you rotate it and look from the sides, you start seeing the world with a certain frequency. For example, you may rotate, you may look at it, you may have a ventilator. What was it in English? A fan, yes. You know, there is a thing with language. If you know that the other person will understand Russian, you just come up with Russian words. Anyways, fan, right? So there's a fan, and you start looking at it with a stroboscope, and you see the fan stop at a certain frequency of the stroboscope. So that's what we are doing with this system. We are looking at the system every 2 pi steps. That's the Poincaré section. Like there is this x of the system, x dot of the system, but time is on a torus. Do you see it? So if we just run the system throughout a very long time, then just look at this cut of the system. Just like the way we did with Lorentz. If you remember, it was a three-dimensional thing. We were looking only at the tops, right? Now we have run, actually at the beginning, we run the system for a very long time. Actually, million steps, right? Then we go ahead and what are we doing here? Can you help me out? Okay. We choose a certain time here. We choose a certain time. Let's say I choose this particular section. Every time the time is nearby that section, I just plot wherever the system is. Okay? And I get this nice graph. But then I start moving this region ahead. So I start moving it around. Like I get a section, I plot a section over here, I plot a section over here, section over here, section over here, section over here. And as you can see, every 2 pi steps, it actually repeats. So I start seeing how this dough making is happening in this double well oscillator, because okay, let's watch it again. So you can see that once it comes on top of this attractor, do you understand what we are looking at? It's a mosaic cake. It's a mosaic cake in 3 dimensions. We'll look at this part, and this part and this part are related, right? Because it's a cake, it's not completely different thing. Like there is some chocolate here, then you expect some chocolate there in the next slice as well, but then that chocolate can go away, right? But here, chocolates don't go away. They are connected by paths. So it's like you see, as you go ahead and come back, as you go ahead and come back, you see chocolate being stretched and brought up here and then stretched again, etc. Are we happy? Yes? It's not always chaotic. I mean, these are particular parameters. So what is this, for example? Let me just look at the whole code. And this is not interesting. This one may be interesting, yes. Let me run that one. Okay. What's going on here is that I start at the, so I have x and x dot, and I have time, right? So I just, at the beginning, I call everything on the right to be yellow, everything on the left to be blue, whatever this color is. And then I let the system run and see where the colors go. And you can see this folding and stretching, folding and stretching, making that mosaic cake. Are we happy? Yes? It's basically a mapping that happens as a flow. You take a dough. Yeah, that's what these equations are doing to the system. But if we are not in the chaotic regime, I guess, for example, 0.2 wouldn't be a chaotic regime. I'm wondering, I don't know what will happen. I'm wondering what will happen.
It's like it's slowed.
Are we still in the chaotic regime? Maybe we are. Let me see. We can only understand it from here. Did I say 0.1 or 0.2? Ah, okay. Let's try 0.1. Okay, this is not chaos. So let's try 0.1 there. If it doesn't work, we just go home. No worries. That this is not going to chaos, right? We just don't have, okay. Yes, this is not going to chaos. You see it, right? It's just, we just mix the cake a little bit, not too much. Okay, very good, very good. A lot of things to play with. What is this one? And this is just Feigenbaum thing. I'm pretty much done with this chapter. If you have any questions, please ask. No? No questions? Should we call it a day? Very good. Bye-bye.